we'll tackle a problem that powers many real-world applications: the proximity service. Whether you're searching for nearby restaurants on Yelp, looking for a hotel in a new city, or trying to find the closest gas station on Google Maps, a proximity service is behind the scenes making it all happen. Our goal is to design a system that efficiently returns nearby places, such as shops, cafes, or hotels, based on a user's current location. But as we'll see, this seemingly simple functionality brings up several nuanced system design challenges. We'll break down the problem, explore how to handle moving users, indexing strategies for fast lookups, and architectural patterns for scalability and low latency responses. Let's get started with the problem statement. The problem is to design a proximity service for nearby places like restaurants, hotels, etc. Here are some good requirement questions to ask. Can a user specify the search radius? How does business information get added, deleted, updated? How do we deal with the case that the user keeps moving? What's the DAU? Let's walk through the high-level components of our proximity service, which supports functionality like finding nearby places, viewing place details, and managing place data. APIs. We start with our API layer, which exposes standard REST endpoints. A GET API to fetch nearby places based on location. Another GET endpoint to retrieve detailed information about a specific place. A POST to add a new place to the system. A PUT to update details of an existing place. And finally, a delete endpoint to remove a place. These APIs are stateless and scale horizontally behind a load balancer. Traffic patterns. Our system is read-heavy. Users frequently request nearby places and place details. Writes, like adding or updating places, are less frequent. This informs our choice of database optimizations and caching strategies. Data model. At the core, we have two main tables. The place table, which stores metadata for each place, like name, address, category, and so on. The GeoIndex table, which supports spatial indexing to efficiently find places near a specific location. Place service. This service acts as the application logic layer. It processes API requests, queries the database, applies business logic, and returns results. It also interfaces with the location-based service. Location-based service. This is a specialized module responsible for geospatial operations, like computing distance between coordinates or querying nearby places within a radius. We'll dive deeper into this component in a later slide. Database cluster. We store data in a distributed relational or NoSQL database cluster that supports geospatial indexing. It ensures high availability and fast query execution, especially for read operations. Overall, this architecture ensures scalability, responsiveness for location queries, and ease of management for place data. We'll start with the 2D search using SQL. This is the most straightforward method where we write a naive SQL query with a latitude and longitude bounding box. While simple, this approach is inefficient and doesn't scale well. To improve on that, we can use a grid-based partitioning strategy. However, if places are unevenly distributed, which is often the case, evenly divided grids don't perform well, as some grids are too sparse and others are overloaded. This leads us to geohashing, which is a popular technique. It transforms the 2D location space into a 1D alphanumeric string by recursively subdividing the map. Typically, 4 to 6 characters provide a good balance between precision and performance. The key idea is that locations with longer shared prefixes are geographically closer. However, it has boundary issues. 2 nearby points could fall into separate geohashes and appear unrelated. A common mitigation strategy is to shorten the hash when there aren't enough results, effectively enlarging the search area. Geohashing is easy to implement and index updates are efficient, but it lacks dynamic adaptability to varying place densities. Next, we consider quad trees. These divide space into 4 quadrants recursively until each node contains a manageable number of places. They are entirely in-memory and well-suited for radius or k-nearest neighbor searches. For nearby searches, we start at the root and traverse down to the leaf node for the query point. If it doesn't have enough places, we explore neighboring nodes. They're adaptive and can scale well with uneven data, but they are more complex to maintain. Building the tree takes time, so we should roll out updates incrementally across our servers. Since places don't change rapidly, this update latency is acceptable. Finally, we have Google's S2 geometry. This maps the Earth's surface to a 1D space using a Hilbert curve, enabling efficient proximity and range queries. It can cover arbitrary geographic regions with high granularity. The region cover algorithm enables flexible and precise control over the search space. Like quad trees, S2 is in memory and offers a more mathematically rigorous way to handle global geospatial queries. We'll choose our indexing technique based on the trade-off between performance, flexibility, and ease of update for our specific use case. On this slide, we dive deeper into the architectural design of our proximity service. 1. Geospatial Index Table. We use a geospatial index table that maps geohash prefixes to place.ids. This table is relatively small, typically just a few gigabytes, so sharding isn't necessary. For performance, we deploy read replicas to support high-throughput lookups, especially under read-heavy workloads. 2. Caching. To improve response time and reduce load on our databases, we implement 2 levels of caching: a cache mapping geohash, list of placeids, for quick lookups by location; another cache for placeit, place object, so we don't hit the DB for full place details repeatedly. 3. Region and availability zones. We deploy the system across multiple availability zones for fault tolerance and to meet region-specific privacy regulations. This helps us remain compliant while ensuring high availability. 4. Filters. Users can filter nearby results by time, e.g., currently open places, or type, e.g., cafes, gas stations. This is handled at the ranking stage after fetching the nearby place data. 5. Workflow summary. Let's walk through a full request. The client sends a location and search radius. The request goes to the load balancer, which forwards it to the location-based service, LBS. The LBS calculates an appropriate geohash precision for the given radius and includes neighboring geohashes to account for edge cases. For each geohash, the LBS queries a Redis cache to fetch place IDs. This is done in parallel for speed. Once it has the place IDs, it fetches the corresponding place objects from the place info Redis cache. Then it computes distances, applies filters, ranks results, and returns the final list of nearby places to the client. This architecture balances performance, accuracy, and scalability, making it suitable for a global scale proximity service.